is from the section labeled atomic structure. Okay, so the question is, the energy of a photon is greatest in the case of A, X-rays, B, ultraviolet radiation, C, visible light, and D, infrared radiation. So there's a few things to know here. First off, it's helpful to know the equation E equals HF, which is just the direct proportion of energy with relation to frequency. As energy increases, frequency increases, or vice versa. Another thing that's good to know is that to know just your um, basic photon um, rays, which is the X-ray, which has the highest frequency, UV, which has lower, visible lower, infrared lower, then microwaves, which is lowest. So if you know that, then you know that X-ray has the highest frequency, which in relation has highest energy. So your answer is A, X-rays. Okay, the next question is about the molecular structure and the bonding. That's the section name. So the question is, for which molecule can the bonding be described in terms of sp3 orbitals of the central atom? Okay, and the options are A, SF6, B, BF3, C, PCl5, and D, NH3. So I already drew out the Lewis dot diagrams, and as you can see, SF6 has 1, 2, 3, 4, 5, 6. It has 6 electron groups. PCl5 has 1, 2, 3, 4, 5. So we have 6, we have 5, we have, for BF3, we have 1, 2, 3, we have 3, and for NH3, we have 1, 2, 3, and 4 because of the lone pair over there. So, so that's 4. Okay, so sp3, it's asking for the amount of orbitals, which is the same thing as your groups. So there's 1 s orbital and 3 p orbitals. So that's 4 orbitals, which equals 4 groups, basically. And the only one that has 4 groups is NH3. So it's as easy as that. D's your answer. Okay, so the next section is stoichiometry, and the question is, what is the empirical formula for the substance with this analysis? It gives us an analysis which shows us Na is 54%, B is 8.5%, oxygen is 37.5%, and this is all by mass. And our options are A, Na3BO3, B, Na2B2O3, C, Na4BO4, or D, Na3B2O2. So I did some work on the side. You basically just change those into grams, basically. You could consider it like, well, it's analysis by mass, so you could just change the percent to G, just to make things easier. It's just a ratio of mass. So we use like 54 grams of Na, and then I converted that to moles using its molar mass. And then I did the same thing for boron and oxygen using 8.5 grams of boron and 37.5 grams of oxygen. So after I converted the mass to moles, I got 2.5 2.4 moles of Na, 2.4 moles of oxygen, and zero point 0.8 moles of boron. I wrote that down here with the subscripts of the amount of moles. So Na subscript 2.4, B subscript 0.8, and oxygen subscript 2.4. Now you just divide it by your lowest amount of moles, which is 0.8. And then you'll get the molar ratio, which ends up being Na3, B1, and oxygen 3. And you look at your options, and oh, there it is. Option A. Okay, so this section is the states of matter / solutions. And the question is, what is the melting point of the pure substance Z? They give us a phase diagram for substance Z with pressure on the y-axis and temperature on the x-axis. So the trick is knowing what is what in each of these sections. So this section is solid, this section is liquid, and this section is gas. And you're asked for a melting point. Now that usually means from solid to liquid, so that transition there. So, and you know that it will make that transition between these temperatures, 0 and 10, just based on your observations from the graph. So, all you do is look at your temperatures between 0 and 10, and 4 degrees Celsius is your only one that falls between that. So B is going to be your answer. Okay, the next section is energetics, and the question is, a 10-gram sample of silver is heated to 100 degrees Celsius and then added to 20 grams of water at 23 degrees Celsius in an insulated calorimeter. At thermal equilibrium, the temperature of the system was measured at 25 degrees Celsius. What is the specific heat of silver? So I wrote down what was given. You have the mass of silver, the temperature, the initial temperature of silver, the final temperature of silver. You have the mass of water, the initial temperature of water, and the final temperature of water. And then the specific heat capacity of water, it should be given to you, but if not, just try to memorize it. It's 4.184. Okay, so the main thing to realize in this is that the change of heat is equal for both silver and water. So that's why I wrote Q1 equals Q2. And this equation is something that you just need to memorize. It has to do with the relationship of mass, heat, and change in temperature, and specific heat capacity. It's Q equals MC delta T. So you set Q of silver equals Q of water. That means the mass of silver times the specific heat capacity of silver times the change in temperature of silver equals the mass of water times specific heat capacity of water times change in temperature of water. Now you just plug in what you were given. You get CS equals 0.022. So your answer is B. Okay, next section is descriptive chemistry / periodicity. And the question is, which of these elements is predicted to be the most active nonmetal? And they give us a list, they give us a table with unknowns Q, R, T, and X, which are assumed to be nonmetals, and electronegativities 0.9, 1, 2.8, and 3.0. So the key thing with this question is you need to know that attract electrons together, that's electronegativity. And you also need to know that the more electronegative is also translates as the most active. So really you could just cross out active and put electronegative. It would give you the same answer. And the answer based on that is X, which has electronegativity 3.0. So your answer is D. Okay, the last section is laboratory chemistry. And the question is, the mass spectrometer may be used to A, detect the presence of isotopes, B, increase the mass of atomic nuclei, C, electrolyze water, and D, separate different wavelengths of light. So now you're going to want to, with questions like these, you're going to want to, you have to look at what the device is called. Now, mass spectrometer. So it spectrometers, I'm assuming it measures something, and mass is the first word. So I know it has something to do with mass. Now, knowing that, I can assume that C and D are out of the question, and those don't really have anything to do with mass. So it's down to A and B: detect the presence of isotopes and increase the mass of atomic nuclei. Well, to increase the mass of atomic nuclei, you would have to add protons. You would need a device that's a nuclear device, not a measuring device. So I think given that, I could also count B out, but just in case, I want to look at A. Detect the presence of isotopes. So this device probably measures mass, and isotopes have to do with like there's multiple isotopes of every element, and if you add or subtract neutrons which have mass, it'll give your element a different resulting mass. So because you measure your mass by adding the neutrons and the protons. So I think something that can measure the mass can help you tell if there's more or less neutrons. My educated answer is that it will be A, detect the presence of isotopes.